Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module The Sturmian Theory from paper Mathematical Tools for Materials. So students, let us see what we are going to learn in this module. In this module, Sturmian theory is introduced. A self-adjoint linear differential system is defined. How any system can be converted into self-adjoint form is explained. The separation theorem and Strom's fundamental theorem are stated and proved. Condition for the solution to be oscillatory is also obtained. Next, the first comparison theorem, the second comparison theorem, and the Sturm's oscillation theorem are proved. The theory developed above is applied to the Sturm-Liouville system. Let us now begin with the Sturmian theory. We had seen that the initial value problem given by the equation y double prime plus p of x into y prime plus q of x into y is equal to f of x with the initial conditions y of x naught is equal to y naught and y prime of x naught is equal to y naught prime has a unique solution provided certain conditions are satisfied. The existence theorem does not supply any information on the nature of the solution. The nature of the solution is of crucial importance, especially in physics. In particular, what interests us is the number of zeros of the solution in a given interval. This is intimately related to the question of the existence of the eigenvalues. This is the problem that we wish to explore now. It was first studied by Strom and is generally called the Sturmian theory. Let us discuss about the self-adjoint linear differential system. The general form of the linear second-order differential expression is L of u is equal to p times u double prime plus q times u prime plus ru. The adjoint of this expression is defined as L of v is equal to p times v double prime plus v prime into within the brackets 2p prime minus q bracket close plus v into within the brackets p double prime minus q prime plus r bracket close. A necessary and sufficient condition that the form be self-adjoint is given by the following theorem. The theorem states that the equation represented by p into u double prime plus q times u prime plus ru is equal to 0 where p, q, r are continuous and p is positive can always be put in a self-adjoint form. Now, the proof is given as follows. Let capital P of x is equal to e raised to power integral of small qx by small px gx. This implies the first derivative of the function capital P of x is equal to a function capital P of x multiplied by small q of x divided by small p of x. Here, capital P is positive and p prime is continuous on the interval a to b. We divide the equation by small p and multiply by capital P. To get p of x into u double prime plus p of x into q by p into u prime plus p of x into r by p into u is equal to 0. This implies within the brackets p of x into u prime bracket close prime plus p of x into R by P into U is equal to 0. Since function capital P of x is positive throughout, therefore the solutions of this equation are the same as those of the original equation. Hence, the theorem has been proved. Now let us consider an example represented by the equation y double prime plus 5y prime plus 6y is equal to 0. This implies p of x is equal to e raised to power 5x, which implies e raised to power 5x into y of double prime plus 5 into e raised to power 5x into y of prime plus 6 into e raised to power 5x into y is equal to 0. This implies y double prime plus 5 times y prime plus 6y is equal to 0. The equation can also be expressed as within the brackets e raised to power 5x into y prime bracket close the prime of the entire bracket plus 6 e raised to power 5x into y is equal to 0. Next we discuss about the Sturmian theory. Since we have proved that linear second order differential equation can always be put in a self-adjoint form, we assume that the given expression is already in self-adjoint. We now analyze the self-adjoint equation represented as L of y is equal to within the bracket function small p of x into y prime bracket close the prime of the entire bracket minus q of x into y is equal to 0. Let us number this equation as equation number 1, where p of x and q of x are real continuous function of real variable x in closed interval a to b, and px does not vanish anywhere in the finite interval a to b. So, we let that p of x is greater than 0. We now proceed to discuss the separation theorem. The separation theorem states that first, no non-trivial solution of the equation L of y is equal to 0 can have infinite number of zeros in the interval a to b. Secondly, all the zeros of a solution are simple. Third, zeros of linearly independent solutions of the equation L of y is equal to 0 alternate. We will now discuss the proof of the separation theorem. First, suppose there are an infinite number of zeros. Then these zeros will have at least one limit point, say x bar. This is Bolzano-Weierstrass theorem. Select a subsequence xi of the zeros so that limit I tending to infinity xi is equal to x bar. Then 0 is equal to limit I tending to infinity y of xi is equal to y of x bar. Further, y prime of x bar is equal to limit I tending to infinity y of xi minus y of x bar divided by xi minus x bar. This is equal to 0. Hence, by uniqueness theorem, it follows that y of x is equal to 0. If a could be a double zero, then y of a is equal to y prime of a is equal to 0, which implies that y is equal to 0. Now assume that one of the solutions, say y1, has at least two zeros x0 and x1, where x0 is less than x1. Then y2 of x0 cannot be 0 because then the Wronskian W of y1, y2 is equal to 0 at x is equal to x0. Similarly, y2 of x1 cannot be 0 Since x0, x1 are consecutive zeros of y1, it does not change sign between x0 and x1. Without loss of generality, we assume that y1 of x is greater than 0 for x lying between a to b. Since y2 of x0 cannot be 0, we assume that y2 of x0 is greater than 0. Now the Wronskian W of y1, y2 at x is equal to x0 is equal to minus y1 prime of x0 into y2 of x0. Similarly, W of y1, y2 at x is equal to x1 is equal to minus y1 prime of x1 into y2 of x1, where y1 prime of x0 is greater than 0, which implies W of x0 is less than 0. Now, the Wronskian cannot change sign between x0 and x1, but y1 prime of x1 is less than 0. This implies that y2 of x1 is less than 0. Hence, y2 changes sign at least once between x0 and x1. By interchanging the roles of y1 and y2, it follows that there is at least one zero of y1 between two zeros of y2. In other words, zeros of y1 and y2 separate one another. This theorem does not hold if the solutions are not real. For example, for equation y double prime plus y is equal to 0, roots of sine of x and cos of x alternate, but not of sine of x and exponent of ix. Let us now discuss the Sturm's fundamental theorem. The Sturm's fundamental theorem states that if there are two functions of x, say u and v, and if u has more zeros than v in the interval a to b, then u oscillates more rapidly than v. For example, if n is greater than m, then cos nx oscillates more rapidly than cos mx. The separation theorem thus roughly states that two linearly independent real solutions of a given differential equation oscillate equally rapidly. If in any interval a particular solution has no or one zero only, it is said to be non-oscillatory. The Sturm's fundamental theorem states that if the solutions of d by dx within the brackets p of x into dy by dx bracket close minus q of x into y is equal to 0 oscillate on the interval a to b, they will oscillate more rapidly if p and q are diminished. Now, let us prove the Sturm's fundamental theorem. First, consider the case when only small q is diminished and small p is remaining unchanged. Let u and v be respective solutions of the equations given by d by dx within the brackets p of x into du by dx bracket close minus q1 of x into u is equal to 0. Another equation is d by dx of within the brackets p of x into dv by dx bracket close minus q2 of x into v is equal to 0. We multiply first equation by v and second equation by u, subtract them and integrate the equation between points x1 and x2 to obtain the equation within the square brackets p multiplied by within the circular brackets u prime into v minus v prime of u bracket close square brackets close limits x1 x2 is equal to integral from x1 to x2 q1 minus q2 uv dx. This is a special case of what is usually called Green's formula or theorem. This is a special case of what is usually called Green's formula or theorem. Let the limits of integration be two consecutive zeros of u. Now suppose that v has no zero between x1 and x2. Take u and v to be positive in that interval. The RHS of the equation is then positive. On the left hand side, the second term does not contribute since u is 0 at x1 and x2. Further, u prime changes sign between x1 and x2 and v is positive at both the limits. Therefore, the left hand side of the equation is negative and this leads to a contradiction. Hence, v must vanish at least once in the interval x1 and x2. In particular, if x1 is a common zero of u and v, the next zero of v appears before the next zero of u. Hence, v oscillates more rapidly than u. We now take up the general case, which is also sometimes called the Strom-Pecan theorem. In this case, the two equations are given by d by dx of within the brackets p1 of x into du by dx bracket close minus q1 of x into u is equal to 0. d by dx of p2 of x into dv by dx bracket close minus q2 of x into v is equal to 0, where p1 is greater than equal to p2 and q1 is greater than equal to q2. Let us evaluate the expression d by dx of within the square brackets u by v multiplied by within the circular brackets p1 u prime v minus p2 uv prime, circular brackets closed, square bracket closed. So, d by dx of within the square brackets u by v into within the circular brackets p1 u prime v minus p2 uv prime, circular brackets closed, square brackets closed, on differentiation simplifies to d by dx of u by v within the circular brackets p1 u prime v minus p2 u v prime, circular brackets close, the entire thing is in square brackets. This is equal to q1 minus q2 times u square plus p1 minus p2 times u prime square plus p2 into within the brackets u prime v minus uv prime by v brackets close square. This implies within the square brackets u by v into within the circular brackets p1 u prime v minus p2 uv prime, circular bracket close, square bracket close, when the limits x1 and x2 is equal to the integral from x1 to x2 within the square brackets q1 minus q2 into u square plus p1 minus p2 within the brackets into u prime square plus p2 into within the brackets u prime v minus uv prime by v, the brackets close, square, square brackets close, dx. This is known as Pecan's formula. Let x1 and x2 are two consecutive zeros of u, and suppose nu is not 0 in the closed interval x1 to x2. Then the right hand side of the Pecan formula is positive, but the left hand side is 0. Hence, there is a contradiction which implies that we must have at least one zero in x1 and x2. The theorem is true even if v is 0 at one or both the endpoints. Suppose v is 0 at x1. In that case, the expression u by v on the left hand side of equation takes the indeterminate form 0 by 0. So, we apply the L'Hospital's rule and replace u by v by the limiting value of u prime by v prime. This quantity is not indeterminate since u prime v prime cannot be 0 where u v are. Hence, limit x tending to x1 within the square brackets u by v multiplied by within the circular brackets p1 u prime v minus p2 u v prime circular brackets close square brackets close is equal to within the brackets p1 minus p2 brackets close into u prime at the point x is equal to x1 will be equal to 0. The same is true if v is 0 at the other limit x2. Thus, if v is 0 at x1, then it becomes 0 again before x2. Hence, v oscillates more rapidly than u. We now wish to find conditions on the function px and qx for the existence of oscillatory solutions to equation 1 in the interval a to b. The functions p and q are continuous and bounded in a to b. Also, p of x has no 0 and has been taken to be positive throughout the interval a to b. Let the upper bounds on p and q in this interval be p1 and q1 and lower bounds be p0 and q0 respectively. Thus, p will be greater than equal to p0 but less than equal to p1. Similarly, q will be greater than equal to q0 but less than equal to q1. First, consider the comparison equation given as d by dx of within the brackets p0 dy by dx bracket close minus q0 times y is equal to 0 or d2y by dx square minus q0y by p0 is equal to 0. The solutions of equation 1 do not oscillate in the interval a to b more rapidly than those of above equation, but the solutions of this equation are known. First, if q0 is greater than 0, the solutions are y is equal to e raised to power plus minus square root of q0 into x by p0, which have no zeros on the real x's. Secondly, if q0 is equal to 0, the solutions are y is equal to ax plus b, which has only one zero on the real x's. Third, if q0 is less than 0, the solutions are y is approximately sine of square root of minus q0 by p0 into x and y is approximately given by cos of square root of minus q0 by p0 into x. The interval between the consecutive zeros of either solution is pi into square root of minus p0 by q0. Putting all this together, we get the condition that the solutions of equation 1 are non-oscillatory if minus q0 by p0 is less than pi square by b minus a whole square. Now consider the other comparison equation given as d by dx of within the brackets p1 into du by dx bracket close minus q1 into u is equal to 0. The equation may be simplified as d2y by dx square minus q1 by p1 into y is equal to 0. The solutions of equation 1 will oscillate at least as rapidly as of equation above. If q1 is less than 0, the solutions of this equation are oscillatory, hence so are the solutions of equation 1. The interval between the consecutive zeros of above equation is pi into square root of minus p1 by q1. Hence, a sufficient condition for the solutions of equation 1 to have at least n zeros in the interval a to b is minus q1 by p1 is greater than equal to pi square into n square by b minus a whole square. We now discuss the first comparison theorem. We consider the systems d by dx of within the brackets p1 of x into du by dx bracket close minus q1 of x into u is equal to 0. The initial conditions are specified as u of a is equal to alpha 1 and u prime of a is equal to beta 1. Another equation is d by dx of within the brackets p2 of x into dv by dx bracket close minus q2 of x into v is equal to 0. The initial conditions are v of a is equal to alpha 2 and v prime of a is equal to beta 2. We are given that p1 is greater than equal to p2 is greater than 0. Also, q1 is greater than equal to q2. We assume that alpha 1, beta 1 are not both 0 nor are alpha 2, beta 2. Further, if alpha 1 is not equal to 0, then p1 into beta 1 divided by alpha 1 is greater than equal to p2 into beta 2 divided by alpha 2. This implies alpha 2 is not equal to 0. Thus, Strom's first comparison theorem states that if u of x has m zeros in the interval x lying between a to b, then v of x has at least m zeros in the same interval and the ith zero of v of x comes before the ith zero of u of x. We now prove the Strom's first comparison theorem. Let x1, x2 and so on till xm be the zeros of u of x in the interval ab. We assume that a is less than x1 is less than x2 is less than so on x till xm is less than equal to b. Then, according to Strom's fundamental theorem, between any two consecutive zeros of u, there lies at least one zero of v. If there is a zero of v between a and x1, the theorem stands proved. If a is a zero of u, then u of a is equal to alpha 1 is equal to 0, then there is a zero of v between a and x1 and the theorem is proved. So, let us assume that u of a is equal to alpha 1 is not equal to 0. Then, since v of a is equal to alpha 2 is not equal to 0, we can use pecan formula. Within the square brackets, u by v multiplied by within the circular brackets p1 into u prime v minus p2 into uv prime circular brackets closed, square brackets closed within the limits a and x1 is equal to the continuous integral from a to x1 within the square brackets q1 minus q2 into u square plus p1 minus p2 into u prime square plus p2 into within the brackets u prime v minus uv prime by v brackets close square, the square brackets are closed gx. The integral on the right hand side is obviously positive. However, the quantity on the left hand side is minus u of a divided by v of a into within the circular brackets p1 of a, u prime of a, v of a minus p2 of a, u of a, v prime of a circular brackets closed is equal to minus u square of a into within the brackets p1 of a into beta 1 by alpha 1 minus p2 of a into beta 2 by alpha 2 brackets closed. By virtue of the assumptions, we have p1 beta 1 by alpha 1 is greater than equal to p2 beta 2 by alpha 2. So that left hand side is negative, that is, it is less than 0. This leads to a contradiction, and hence mu must have a 0 between a and x1, and hence the theorem is proved. We can put the result in a different way as well. If the zeros of the solution of the differential system given by d by dx of within the brackets p of x into du by dx bracket close minus q of x into u is equal to 0 with the initial conditions u of a is equal to alpha and u prime of a is equal to beta are marked on the real line from A to B, then the effect of diminishing P and Q without changing alpha and beta is to shift all the roots in the direction from B to A, that is, from right to left. When P and Q are reduced continuously, a stage may arrive when a new zero enters the segment from the right. The new zero will first appear at B and then move into the segment. We next discuss the second comparison theorem. Let C be any interior point of the interval A to B which is not a zero of either U or V. The second comparison theorem states that if C is such that U and V have the same number of zeros in the interval x lying between A to C, then P1 of C into U prime of C divided by U of C is greater than P2 of C into V prime of C divided by V of C. We now prove this theorem. Let xi be the zero next before C. It is necessarily a zero of U but not of V. For between A and xi, there are exactly I zeros of V and ith zero of V must precede xi. Then by pecan formula applied between xi and C, we get within the square brackets U square multiplied by within the circular brackets P1 U prime by U minus P2 V prime by V circular brackets close, square bracket close, with the limits xi to C is greater than 0, which implies P1 of C into U prime of C divided by U of C is greater than P2 of C into V prime of C divided by V of C. Hence, the second comparison theorem is proved. We next proceed towards the Strom's oscillation theorem. We now look at the differential system with 2-point boundary conditions. L of y is equal to within the brackets p of x into y prime bracket close, then the prime of the bracket minus q of x into y is equal to 0. Alpha times y of a minus beta times y prime of a is equal to 0 and gamma times y of b plus delta times y prime of b is equal to 0. Let us number these equations as true. When the first boundary condition is imposed on the general solution, we obtain only one distinct solution given as y is equal to a function capital Y of x and lambda, where lambda is some parameter appearing in P and Q. When the second condition is also imposed on this solution, we obtain a relationship involving lambda. F of lambda is equal to gamma times function capital Y of B lambda plus delta Y prime of B and lambda is equal to 0. The roots of this characteristic equation are the characteristic numbers or eigenvalues. These are the values of the parameter for which the 2-point boundary problem has a non-trivial solution. The solutions are called the characteristic functions or eigenfunctions. As we have seen in the conditions for existence of oscillatory solution, if for some lambda minus q by p is greater than equal to m square into pi square divided by b minus a whole square, where capital Q and P are the upper limits on small q and small p respectively, then for that lambda, the equation admits of a real solution satisfying the first boundary condition above and having m zeros in the interval a to b. If the further condition that minus capital Q by capital P tends to infinity for lambda is equal to for lambda tending towards Greek lambda 2 is imposed, then the following theorems can be proved. Theorem 1. The system described by equation 2 has an infinite number of real eigenvalues which have no limit point but Greek lambda 2. For each integer m is greater than equal to I, there exists one and only one eigenvalue lambda m plus 1 to which corresponds a solution having m plus 1 zeros in the interval a to b. If capital P prime and capital Q prime are the lower limits on small p and small q, then with the further assumption minus of capital Q prime by capital P prime tends to 0 for lambda tending to Greek lambda 1. We then get the second theorem. This is theorem 2. The real eigenvalues of the system described by equation 2 may be arranged in increasing order of magnitude and denoted by lambda naught, lambda 1, lambda 2 and so on, lambda m and continues. If the corresponding eigenfunctions are y0, y1, y2 and so on, ym, then ym will have exactly m zeros in the open interval a to b. The condition above is explicitly for the purpose of obtaining a lower limit lambda naught on the eigenvalues. This condition, though sufficient, is not necessary. There is an alternative set of sufficiency conditions which ensures the existence of the lower limit lambda naught. Let us now discuss the application to the Sturm-Liouville system. The Sturm-Liouville system is represented by the equation within the brackets p of x into y prime bracket close prime plus within the brackets lambda multiplied by g of x minus L of x bracket close into y is equal to 0. A times y of a minus beta times y prime of a is equal to 0. Gamma times y of b plus delta times y prime of b is equal to 0. Here, lambda is a parameter which is quite often the energy or frequency. P, G and L are real continuous functions of x in the interval a to b independent of lambda. P and G are positive throughout the interval. The coefficients alpha, beta, gamma and delta are all independent of lambda. Since Q of x is equal to 1 minus lambda of g steadily decreases for any x in the interval a to b as lambda increases from Greek lambda 1 is equal to minus infinity to the Greek lambda 2 is equal to infinity, the conditions of theorem 2 above are met. In particular, minus q is equal to minima of within the brackets lambda times g of x minus L of x bracket close tends to plus infinity as lambda tends to plus infinity. Consequently, there exists an infinitely set of eigenvalues lambda naught, lambda 1, lambda 2 and so on continue till lambda m and so on. And if the corresponding set of eigenfunctions are y0, y1, y2 continuing till ym and so on, then ym has exactly m zeros in the open interval a to b. If for lambda equal to 0, we impose the additional conditions L greater than equal to 0, alpha beta greater than equal to 0, gamma delta greater than equal to 0, then Greek lambda 1 may be taken to be 0. In this case, when lambda is 0, minima L is greater than equal to 0 and the eigenvalues are all positive. This is true in many physical applications where lambda is often related to the energy. Now consider the other important case in which P is greater than 0, L is greater than equal to 0 and G changes sign in the interval A to B. We rewrite equation 3 as within the brackets P of x into y prime divided by modulus of lambda brackets close. Now the prime of the entire bracket minus within the brackets L of x minus lambda times g of x brackets close into y divided by modulus of lambda is equal to 0. It is now of the form of equation 2 with P tending to P by modulus of lambda and Q tending to L of x divided by modulus of lambda minus g of x, where lambda is greater than 0 and P tending to P by modulus of lambda and Q tending to L of x by modulus of lambda plus g of x if lambda is less than 0. In either case, P and Q steadily diminish as modulus of lambda increases. Up to the present point, the required conditions are satisfied. But if we note that capital Q is greater than 0 and capital P is greater than 0, then minus of capital Q by capital P tends to minus infinity as mod of lambda tends to infinity. Thus, the conditions of theorem 1 above are not satisfied. However, since the conditions are sufficient but not necessary, it does not follow that the theorem is false. Since G changes sign in A to B, a subinterval A prime B prime can be found in which G is greater than 0 for lambda greater than 0 or G is less than 0 for lambda less than 0. In either case, values of modulus of lambda may be taken to be sufficiently large to ensure that L minus lambda G is less than 0 in the interval A prime B prime. Consequently, the required condition minus of capital Q by capital P tends to infinity as lambda tends to infinity is satisfied in the interval A prime B prime. Then the methods of the oscillation theorems may be applied with only one difference, that we have two separate cases, lambda less than 0 and lambda greater than 0. Therefore, the oscillation theorem now takes the following form. If G changes sign in A to B and L is greater than equal to 0, alpha beta is greater than equal to 0, gamma delta is greater than equal to 0, then there exists an infinite set of real eigenvalues which have plus infinity and minus infinity as two limit points. If the positive and negative eigenvalues are arranged in order of increasing numerical values as lambda naught plus, lambda 1 plus, lambda 2 plus, and in this way till lambda n plus. Similarly, lambda naught minus, lambda 1 minus, lambda 2 minus till lambda n minus, and if the corresponding eigenfunctions are y naught plus, y1 plus, y2 plus, and so on till yn plus, and y naught minus, y1 minus, y2 minus, and so on till yn minus, then yn plus minus have exactly n zeros in the interval A to B. So students, let us now summarize what we have learned in this module. In this module, we introduce the Sturmian theory that deals with the nature of solutions of second-order linear differential equations. We define the adjoint of a differential system and condition for the system being self-adjoint and explain how any system can be converted into self-adjoint form. We first state and prove the Sturm separation theorem and fundamental theorem. Next, we obtain the condition for the solution of the equation to be oscillatory. After that, we prove the first and second comparison theorems, which deal with the increase in the number of zeros as the functions p and q are changed. We then take up the Sturm's oscillation theorem, which is the main result of this module. Finally, we applied the theory developed above to the Sturm-Liouville eigenvalue problem. Thank you, students, for your kind attention.